Thank you very much. Thanks for the good words. I'm happy to be here. Nice to see many people who I know, some that I don't know. I've been doing different things over the past, should I say 50 years? I just turned 50. And one of the things is deformation bands. So that's what I'm going to focus on today. And why study deformation bands? Because they are fun structures. They show an interesting range of variations, and they can be studied in the field. They can, of course, also be studied in the laboratory and on the computer, which Karen knows everything about. But it's a good excuse to go in the field and visit nice, interesting places. And they happen to reduce permeability, most of them, which is good because then the oil companies get interested and we can get money to go in the field. And that's all we want to do as geologists, right? So where do we find these structures, deformation bands, little shear zones? Well, we find them in highly porous media, mostly in sandstones, of course. And porosity should be at least 15% as a rule of thumb is what you need to get deformation bands. Places like the western U.S., Colorado Plateau, and other places in the out west. Sinai Peninsula is a good place to look for deformation bands. Southern France, and even not too far from Oslo, there are some examples of deformation bands, and many other places. And in many or most of the old reservoirs, you will find deformation bands. It's just that people don't see them because they are very much of subseismic nature. You do see them in cores, of course. So deformation bands. So there are fractures and there are deformation bands, and I like to make a distinction between the two sets of structures. And but there's, of course, many similarities. For example, when it comes to kinematics or the mode of deformation, we have extension fractures, which form in opening mode, like this. We have shear fractures, and we have another type of sharp discontinuities that are not called fractures, but styloids. So these kind of define the end members of a spectrum of should I say, modes of movements associated with fractures. And the same thing goes for deformation bands. We have the dilation bands corresponding to extension fractures. We have the shear bands, the pure simple shear bands. And we have compaction bands that correspond to styloids. So we have this whole range also for deformation bands. So there is simple shear in some bands. There is even dilation bands, very rare, but have been described. And there are these compaction bands. But for the most part, the deformation bands that we find in most sandstone reservoirs involve some compaction and some simple shear. So it's a combination of the two. And that's nice. When we have compaction, we get reduction in porosity, we get reduction in permeability, and things get interesting. So this is the most common type of deformation band, compactional shear band, compactive shear band that we have. Okay, I'm going to skip that. And then one really important thing that can also be used to classify deformation bands is what happens basically to the grains during deformation, whether we have just sliding and rotational grains, non-cataclastic flow, or whether the grains actually break during the course of the deformation. That makes a big difference, and that's one important factor that we want to know about as much as possible. Okay, just an example of non-cataclastic bands. Those are probably the ones that are closest to simple shear. This is an outcrop in Denmark, Jylland. And these sediments have not been buried very deep. So we see nice shear zones. Sand has been smeared and sheared. The same goes for the clays. So nice non-cataclastic bands. Another example from southern Utah. This is the Entrada sandstone, and the topmost layer is a slick rock. You can see a very planar, straight surface, which is sitting on top of convoluted bedding or beds. Mud trying to escape up, sand sinking in. Typical sedimentary, depositional structures. And if we focus in here, we see lots of small-scale structures, and these are deformation bands. And these are, they look something like this. And you don't really see them very easily in the sandstone, except where you have markers that they offset. And you don't really see them very easily in thin section either. This is one of the bends. And that's the thing about the non-cataclastic bends. They don't really have a great impact on the structure of the rock in many cases. Let's jump to the next one. Another example from sand dunes that have been mobilized at very shallow levels, isoclinal faults, and deformation bands in the same outcrop, soft sedimentary deformation. And you find once you start to look for these kind of structures in for example, Aeolian sandstones, you find them, if not all over the place, at least many places in the western U.S. and other places. And like I said, they don't leave much traces in the sand or sandstone, and you can only see them where there are laminations that is being affected. Nice shear zones. The exception is where you start to get minerals that are platy or have a preferred orientation, or not preferred orientation, but an elongated shape. Then they start to line up and compact, and you get these kind of shear bands that we find many places in the North Sea and Norwegian continental shelf reservoirs, where they actually do involve a reduction in porosity and permeability. Before leaving these non-cataclastic bands, I'm just going to show you a kind of a cool example of another type of tectonics. These people are looking at these structures right here on this line. I don't know if you know what this is. Well, this guy knows. So these are dino tracks, impacts from some kind of, not necessarily this exact, this is the Utah raptor, some kind of dinosaur at least, made these impacts at some point in time in the Jurassic. And if we look at these impact structures kind of things, and it might be hard to see from the back, but there are little shear bands in here. Let's see if we can get a little closer look at one of those, a couple of those. Shear bands, shear deformation bands in the sand. So this is dino tectonics, if you like, and not, as you can imagine, not very pretty shallow depth at the time of deformation. But still, there are deformation bands. So various ways that you can form these features. So during deformation of sand, there's lots of interesting things going on the grain scale. And again, Karen knows much more about this than I do. But I remember some 10 or 15, maybe 20 years ago, we were playing with these cereals, honey grain, I think, putting them into bowls and putting the bowls together and rotating the bowls. And we found that it got harder and harder to rotate the bowls as displacement was accumulating. So if we do this sharing of grains like this, we form these bridges, if you like, which people also call force chains. And that whole process is related to the strain hardening that we often find in deformation bands. And this is also, I mean, these contact points here is where the grains would, oops, not what I wanted, where the grains would fracture most easily. So if the stress and strain gets high enough, we'll start to grow fractures at these locations here, most likely. And that could result in rocks that look something like this after the deformation is over. In this case, pretty shattered grains. These are from the Castle Gate Formation in Utah. So there's various intensities of this fracturing that we can find. The grain fracturing, that's really what we see in many deformation bands. So again, deformation bands and fractures are fundamentally different in many ways. Deformation bands are cohesive. Fractures involve loss of cohesion. So it means that when you form fractures in a rock and you deform it again and brittly, then the rock is most likely to fracture, to split apart along the fractures. Most deformation bands involve a reduction in permeability. Fractures do not. They usually involve enhanced permeabilities, like these fractures, for example, that formed also in sandstone, but after the sandstone was cemented. And it's obvious that fluids have been flowing along these fractures, penetrating the originally bleached host rock, forming these beautiful colored zonation patterns. We find many places in southern Utah, for example. Okay. Deformation bands form in rocks that are highly porous. Fractures form in low porosity rocks, no porosity rocks. And deformation bands also have a measurable thickness that is easy to identify. Fractures are more like surfaces. Let's have a look at this deformation band since it's here. High porosity is very clear from this picture. In between the sand grains, there's pore space. The white thing is the deformation band itself. So if we look at that under a microscope, thin section, it looks, in this case, something like this. This particular one is from Sinai, the Nubian sandstone. Blue is porosity, or pore space. And there's not much blue left in the band itself. So it tells us that porosity has been reduced, and also permeability. So that's a typical cataclastic deformation band. The way we find deformation bands varies. We find, in some cases, we find them as single structures, some places, like this one, with just 1 or 2, maybe 3 centimeters of offset. And then nearby, maybe you find a cluster of deformation band like this one, where there are lots of deformation bands. And in other places, within these clusters, you can find things like this, which is obviously a slip surface. And the slip surface forms then in the middle of a bunch of deformation bands like this. This is so we then have a fault once we see a slip surface like this with, in this case, about 6 meters of offset, but then still deformation bands on each side. You never find a fault in a sandstone like this without deformation bands on each side. What does that mean? The simple explanation, which has been around for a long time, is that faults in sandstone, porous sandstones, initiate by deformation banding before the actual fault plane forms. So if this is a sandstone, and the black lines here are deformation bands, 1, 2, 3, 100,000. And then at some point you reach a saturation level, and the slip surface actually forms, and that's when displacement really starts to accumulate. But then you're stuck with these deformation bands on each side of the fault. So they are kind of precursory structures when it comes to faulting in sandstone. So this is a very different way that faults form, different from how they form in rocks that we have in most places in Norway, for example. And it's a simple but very important observation, piece of knowledge. Cool. So like I think I mentioned, these deformation bands have implications for fluid flow. So that's another property that is important, especially to oil companies. And you can see this this effect in many ways. For example, this is an oil field actually in California, north of Santa Barbara somewhere. And there's a deformation band zone right here, and there's tar-filled sand up there. There's no tar in the sand below the deformation band. So these deformation bands have some control, at least on fluid flow in reservoirs. And we also see that in places like Valley of Fire. I don't know if you've been there. It's some amazing colors, and some of these color patterns that you can see in the sandstones in that state park are, to some extent at least, controlled certainly by bedding, but also by deformation bands. Let me click into this one maybe. This is Bergen Soliva from University of Montpellier. So these are the deformation bands here, bedding. So by introducing deformation bands, you get kind of a second set of anisotropy in the rock in addition to the bedding itself, which is important. And in this case, I think the theory is that meteoric water has been percolating down, hitting the deformation bands, dissolving hematite, and then reprecipitating hematite down dip along the bedding surfaces or beds. At least they have an influence on fluid flow. We can study this also. This is an experiment that we did in Zipper, Bergen, where you can do all these kinds of experiments where you're just flowing fluids into this sample, which is about hand-sized, I don't know, somewhere between 5 and 10 centimeters in length. So if we put fluids in here and we use a kind of a tracer technology so that we can, whoops, it didn't work so well. We can see what's going on, then we can see how the fluid actually is affected by the deformation bands, and we can see that the deformation bands themselves are still white because of their low porosity. So let's do that again. So the way that the fluids cross, so this is one place where the fluid would cross easily, and that's because the deformation band right here is kind of thin right there. So we can study these relationship between deformation band thickness and also the internal structures of deformation bands if we want to, which is a big field. Okay, so the cataclastic deformation bands is what perhaps most people are most interested in because they have the most impact on fluid flow. And they also stand out more in the rocks because they are white and have a positive relief and things like that. So what are the controlling factors when it comes to whether the grains break or just slide and roll without breaking? So obviously there is the state of stress at the grain contacts and also the grain strength, and which is pretty obvious. I mean, when you do these kind of experiments or numerical or optical, you can see how the stress is located, of course, at the grain contact points. That's where stress is transmitted from one grain to the other. And that's where also they will start to fracture. So whether that's going to happen, that depends on basically the overburden, but also on the shapes of these grains. So the area basically of the contact points and things like that, and the type of mineral, strength of the mineral. Let's go back. So the overburden is important. So the example of non-cataclastic bands that I showed formed very close to the surface. There are examples that are deeper down. So this is depth here, compressive and tensile stress conditions. So you form most easily disaggregation bands near the surface, and you tend to get more cataclastic bands deeper down. That's the simple idea. And it's very common to see disaggregation bands, that's non-cataclastic deformation bands, being transected by later cataclastic deformation bands. We see that all over wherever you have these sandstones. And then there's also this thing, when the rock gets down there, it gets cemented, lithified, and on the way back up to the surface, it may even cross into the tensile field because of the cooling and pressure conditions. And you get fractures, which is what we also see when we go to places like the Colorado Plateau. The rock is full of late fractures. So this understanding of this dynamics of the connection between when the deformation happened, the burial curve of a certain locality, and what kind of structures you get is really important. I wasn't quite done with that one. No, I was not. And of course, mineralogy. This is a graph been used by several people. Ferrosilicate content is the mineral, the common mineral in sandstone that is most different from quartz, which is the other really common mineral. And of course, the more ferrosilicate you have in a rock, the less likely you are to form or to break the grains, because of the lubrication effect of ferrosilicate minerals. So depth, if you don't have ferrosilicates, you can get cataclastic deformation pretty close to the surface to some extent. Once you have some ferrosilicate minerals, it's much harder, which is another point. And I don't know. I think okay, let me just show this very quickly. I don't know if you're familiar with this kind of graph. This is the mean stress, sometimes referred to as pressure, and differential stress. And this is the yield envelope for a sand or sediment. So within this stress subspace here, there's only elastic deformation going on. Once you cross or hit this yield envelope, yield cap in this part, it's you're going to basically form deformation bands, permanent deformation. And as the rock compacts, as it gets buried, this envelope is going to change, grow, because it depends on porosity, among other things. And if you then at some point apply tectonic stress, then you're going to increase the differential stress. Now, if you do extension, you're going to reduce the maximum horizontal stress, so you're going to actually move that way to the left in this diagram, something like this, unless you keep burying your sandstone. And you're going to hit this envelope somewhere, most likely somewhere in this region here. That's the idea. And if you keep making deformation bands, you might eventually hit the frictional strength of the bands or the zone of bands and make a fault. Now, if we have contraction, we're just going to add to the horizontal stress by adding the tectonic horizontal force, the stress, and we're going to move in this direction and probably hit the cap farther to the right. And what that means, if this is correct, is that you are likely to get more compaction during the deformation band formation in contractional deformation than in extensional deformation. And then this may grow like that. I'm not going to dwell with that, but we do find compaction bands. So far, we've only found them for contractional deformation, regions of contraction, basically. And just thought I'd show you some interesting examples of that. By going to this structure, this is in southernmost Utah. near the Arizona state line is right down here. This monocline fold is called the East Kaibab monocline. It's one of many basement uplifts. And let's have a section up here. So it looks something like this. Textbook example of a monocline. On the east side of the steep limb, we find highly porous sandstones, and we also find these compaction bands that are really interesting. Let's have a look at those. Well, this is a sandstone example from that area, and we see one set dipping to the left, right, I guess, and one set dipping to the left. So conjugate sets, and these sets involve a little bit of shear and compaction. We call them shear-enhanced compaction bands. So they form conjugate sets. And then there are these structures here. And those do not have any shear offsets along them. So we think they are compaction bands, pure compaction bands. So just perpendicular shortening. And considering these as pure compaction bands also allow you to form all of these structures in one phase of deformation. People have been talking about different phases of deformation here, but I think it's possible just to explain all of these structures with one single phase of contraction. That's cool. Let's have it's always nice to make things simple. By the way, you can also see these early non-cataclastic deformation bands that we talked about before, probably forming at very shallow depths, just a few meters, 10 meters or something like that. And then there are the compaction bands. And these bands are wiggly. They are curved, not well suited for shear along them because of their geometry. So that's another argument that these are actually compaction bands. And if we look at them in thin section under the microscope, these particular ones look like this. This is one wavelength is about 1 centimeter or 2. Well, varies a little bit. And there is some crushing of some grains. There is some dissolution across grain boundaries. So both of those mechanisms operated during the formation. And also note that these bands do not cross this particular, a little bit more fine-grained layer. So they are very, very selective when it comes to where they want to live, basically. They don't occur in all kinds of layers, even though everything here is sandstone. And the same goes for some of these shear bands that have compaction. This is one sand dune unit here with bounding surfaces on the top and bottom, and we can see these deformation bands here being localized to the lower part of the sand dune. I wonder why is that? Well, the porosity is higher in this part of the sand dune because of the way that sand dunes form, with grain flow units, grains flowing down, sorting processes and things, better sorting down here than up here. So there is, it appears an increase in porosity and also permeability as you move from the top of the dune and down toward the base of the dune. The scale is, there's a hand for scale. No, the scale is, these bushes are like this. So this would be maybe 4 or 5 meters base to top. So I just traced some of these. This is again a dune boundary here, dune boundary there, a few meters in between. Deformation bands occur in some layers more than in other layers, in higher frequencies than other layers. And you can represent that on a graph. Horizontal axis, number of deformation bands per meter, so just density. And vertical distance. Then we can go in and measure permeability, which is much quicker than measuring porosity. So, oops. So if we do that, we get a very close match between permeability here and the density of deformation bands. So the higher the permeability, the more deformation bands you see in the sandstone. It's a very close connection. I have another example of the same thing. These are all pure compaction bands. There's a little mix-up here. So density of deformation bands, and these have been measured not across, but along a single force set, if you like, from the top of the dune to the base along the force set. Same force set, same bed. And they look, these beds look very, very homogeneous, but you get more and more deformation bands as you move down the dune, down the slip face. And if we add the permeability measurements, we see that there is an incredibly good match between density of deformation bands and permeability. So actually pretty surprising results. I mean, they look almost fabricated, these graphs, but they are not. Of course, we are scientists. So amazing how this works. Not so much, the connection is not so clear for shear enhanced compaction bands, or at least the range is wider. This is the density up here. We have 16 per meter, 12 per meter, and so on. And permeability, as measured using a tiny mini permeameter. But the highest densities occur where the permeability is highest. And there's a cutoff at about 100 millidarcies in this case, maybe a little bit less. If the permeability is less than that, you don't get deformation bands at all. And like I said, pure compaction bands are more sensitive. And you have to have something like almost 20 darcies, tiny perm darcies, I should say, to see compaction bands at all. And the higher the permeability, the more bands we see along these beds. And that translates into something like 9 or 10 darcies when we correlate this permeability with plug data. And it translates into about 30% porosity. So you need about 30% porosity to form these compaction bands. So that's compaction bands. And it's something that I found interesting. And there are other relationships that you can find in these sandstones. I don't know if you can see. This is a zone of not compaction bands anymore. These are the classical compactional shear bands that were described by people from Stanford in southern Utah, Iden and his students. And the zone is quite thick up here, where it's well-sorted, relatively coarse-grained sandstone. And the width of this zone goes down to almost nothing. It actually turns into a slip surface down here. And then you're down into siltstones and eventually mudstones down at the base. So again, you can see this very clearly. These are very sensitive structures, very sensitive to variations in grain size, porosity, which is connected to permeability. Reason why we use permeability is just it's so easy and quick to measure in the field. We make the connection later. And so it's very interesting to see these relationships, and that's one of the things I'm working on, is to try to sort out these things. So the ultimate goal is to know as much as possible about the relationship between how deformation bands form, where they form, and the lithologic parameters. So if you know then the lithologic parameters from an oil field, for example, the depth of burial and things like that, you might be able to make some useful prediction about these subseismic structures that probably are in the reservoir. So that's the official goal of spending time in the field. There's so many things about deformation. Just I have to mention this. This is the length of a deformation band or fault. These are faults here. The red and blue are deformation bands length, and then there's the displacement, the maximum displacement along that length, which is usually in the middle. And if you plot those two, one against the other, in a log-log plot for faults, you get this kind of trend. Deformation bands behave differently, at least the cataclastic deformation bands do, not the disaggregation bands. But these are cataclastic bands. And they show a different scaling relation between length and Dmax, which is interesting. It actually means, for practical purposes, for oil people, is that faults, if we have this would be 1 centimeter offset, this 1 meter. So let's say a 10 centimeter offset on a fault would be just a few meter length of that fault is what you would predict. For the same offset, the deformation band could be somewhere between 10 and 100 meters, probably closer to 100 meters long. So much, much longer relative to displacement. It's another way that deformation bands are different from regular faults, shear fractures. Okay. And we find deformation bands. That's another thing. Where are they distributed relative to the larger structures? They are, of course, you find them many places, but preferentially near faults that are, in some cases, of seismic size. I mean, you can see them in seismic data. This fault is 150 meters approximately, and you get this zone of deformation bands, which is referred to as the damage zone by most geologists. I actually think this is just there are so many ways you can characterize this damage zone. And since I'm running out of time, I'm not going to dwell with that. I'm going to remind you about this model. So the reason why we find these deformation bands around the faults is because they form actually before the fault is born, and also then after the fault is, while the fault is moving, you add deformation bands for various reasons. Geometric reasons, linking all kinds of fault interaction and things like that. So I'm going to skip that too. So that means, that has several implications. It actually means that you have, where you have a fault, you have a damage zone on each side, but also it gets really interesting when you follow this fault to the very tip point where the slip surface has its tip point. Then there you would expect to find a process zone that extends beyond that tip point. And that's what we find in the field. I'm going to take you to another place in southern Utah, Arches National Park, where we have a fault system in Salt Valley, Cache Valley, I think is the name, where the fault is split into several segments. If we look at this one here, it turns out that it's a nice relay ramp. So one fault dying out to the right, another one taking up the displacement. So it's a transfer or a relay structure. Let's jump down on the ground. Interesting that there are at least 500,000 people hiking up this ramp every year without knowing that they are actually acting like drops of fluids, going from the foot wall, from the hanger wall to the foot wall.
Where is that?
This is one of the main attractions in Arches National Park in southern Utah. Delicate Arch Trail. I mean, this is Delicate Arch up here. I wonder if you can. Let's try to click at that. Click on that. Oh, doesn't work. Yeah. So you're one. Yeah, I did that the first time too. So no worries. Anyway, this is relay ramps. Sorry. Relay ramps are sorry again. Interesting structures. They form as faults grow and pass each other, overlap. And students are good for mapping these things. This is how we imagine this. This is a fault, and these are the damage zone. We imagine there was this front, if you like, the process zone that moved ahead of the actual fault. So Atle Rotevatn, my former student, now colleague, mapped the trends of the deformation bands and found that this ramp is actually full of deformation bands. These are the trends. There are more deformation bands than what this map shows, but these are the trends. And also made a strain, not a strain map per se, but a density map of deformation bands. So we collected all the data, the small-scale data. And once that was done, well, I guess this only shows the two faults and the process zone and the various data from the fault and into the process zone, showing that there is fewer and fewer deformation bands, but you can trace them all the way up there, which is about 350 meters away from the tip point. Okay, once that was done, put it into a reservoir model, putting in as much of that information as possible into a gridded model, and put basically fluids into the hanging wall and an injector well kind of simulated thing up here. So putting the fluids in there made them migrate up the ramp and just around the corner and into this well. And green is where water has displaced oil. Okay, so we have been able to displace a lot of oil from the ramp and moved it into the well. In this case here, the deformation bands do not have a very low permeability. The contrast is not very big between the bands and the host rock. In this case here, it's larger, and what happens then is that the fluids do not just cross just around the corner here. They actually have to move a little bit farther up the ramp and cross over the deformation band zone along a longer stretch, if you like. So you actually get more of the oil out of this ramp structure if the deformation bands have a lower, significantly lower permeability than the host rock. So they're actually contributing in a positive way to getting as much oil out of this piece of the reservoir as possible, which is interesting. They don't have to be negative. So one of the final slides here, I think. So a process zone of deformation bands that is 350 meters, and then there's the subseismic portion of the fault, which you cannot see in seismic data unless you do special things to the seismic data cube. And that's 500 meters of the fault that you cannot really see, that these oil people can't see from their data, that we can tell them that this is something you should take into consideration. Now, the length of the process zone depends on lithological parameters that we've seen that, and there's many complications, but this is a very important message that we send to the oil companies. So that's basically it. Deformation bands, lots of implications, lots of fun things. They deviate from fractures in many ways. They live their own life. They are very sensitive to lithological variations, and there's lots of things to be done still in this field. So I'm looking forward to many more trips to the Western US, I guess. So thank you.